Good evening. So, myself Anjali Prasad. Today we are going to start with the week 10 assignment discussion session. So, we will be starting in within few minutes. Yes, we will do. We will be starting in a few minutes. Just let wait for a few minutes for others to join. Am I audible? Okay. Um. So meanwhile, till others join, let's start with the session. So let's go through the things that have been discussed in this week. So, first of all, um, there have been the discussion about the some results on metric spaces. So it was like, let xt be a metric space and a subset of x, then the function f from x to r such that f of x is equals to d of x comma a. It is continuous. Okay. Next, there was a Lewis number lemma. So what was that? That let xt be a compact metric space and c be an open cover of x, then there is a lambda greater than 0 such that for all x belongs to x, there exists a g belongs to this cover C satisfying d of x comma lambda subset of g. Okay, so that it means that if you have a compact metric space x comma d, and if C is open cover of x forming, then there will exist a lambda greater than 0 such that for all x belongs to x, there will exist such ball with center at x and radius lambda that will be subset of g. Okay, so this is all about Lewis number lemma. Now next there was about uniform continuity. So what was that? That a function f from a metric space xt to the metric space yd dash is said to be uniformly continuous if for a given epsilon greater than 0 there exists delta greater than 0 such that for every pair of points x1 x2 in x, um, d of x1 x2 will be less than delta. That implies d dash of f of x1 f of x2 will be less than epsilon. So okay, so this is a similar definition as in real analysis. So this gives the definition of the uniform continuity. Fine. I hope this is clear. Now, okay. So next is there is uniform continuity theorem. So what is that? So the uniform continuity theorem says that let xt and yd dash be compact metric spaces. Then the continuous function f from x to y is uniformly continuous. Okay. Now next was limit point compactness. That is the Bolzano-Weierstrass property. So what is it? That a topological space x comma tau is said to be limit point compact if every infinite subset of x has a limit point. Okay. Next, there were some results. So, okay, I guess you are known with what is limit point compactness. So it is a topological space is said to be limit point compact if every infinite subset of x has a limit point. Okay. Next, there were some results such that every compact topological space is limit point compact, but the converse is not true. Okay. Now, next says that the continuous image of a limit point compact topological space need not be limit point compact. Okay. Fine. Now let's move to the next topic. So there was a discussion about even spaces. So what is even spaces? So a topological space x tau is T1 if for each pair of distinct points x and y in x there is an open set containing x but not y and another open set. Um, you are asking about an infinite success? Yes, here it is only about infinite subset of x. There is no concept of boundedness. Okay. Okay. Now, what is about T1 spaces? So, a topological space x tau is T1 if for each pair of distinct points x and y in x, there is an open set containing x, um, but not y, and another open set containing y, but not x. That is, if you have a topological space x comma tau, and if you have two points x and y, so there will be two, we will get open sets such that one will contain x and not y, and one will contain y but not x. Okay, so such spaces is called as T1 spaces. So there are some results on that. Okay, so in T1 spaces, we are talking about 2 points, right? For every 2 points, you will get like this. And in T2 spaces, what is there? Yes, in T2 we talk about the disjoint open set, and in T1 we will be having two open sets but may not be disjoint. Okay. Yes, yes. Here it may not be disjoint. Okay. Um. Okay. So there are results. So what they say, a topological space X tau is T1 if and only if every single point subset of X is closed. Let X tau be a topological space and A subset of X, then X belongs to X is a limit point of A if and only if each open set containing X contains infinitely many points of A. Okay. So these are some results on related to T1 spaces and the limit point. Next, there is a result. I am audible, right? Okay. Now, what is countably compactness? So, a topological space X tau is said to be countably compact if every countable open cover has a finite subcover. Okay. So, if for every countable open cover you get finite subcover, then we call it as a countably compact set. Okay. Now there is Lindell of spaces. What is that? What is that? So a topological space X tau is said to be Lindell of if every open cover has a countable subcover. Okay, so if every open cover you get a countable subcover, then we say that it is Lindell of spaces. Fine. Now next there are some results on this. So it goes like first it says that every second countable space is a Lindell of space. Then a Lindell of space is not necessarily second countable, and a Lindell of space is not necessarily compact. Okay. Now, there are more examples like statements like a continuous image of a Lindelof topological space is Lindelof. Then the question space of a Lindelof topological space is Lindelof. Similarly, other points are also there. Fine. Like every closed subsist of Lindelof topological space is Lindelof. Then every countably compact topological space is limit point compact. Then every limit point compact topological space, which is also T1, is countably compact. Now comes local compactness. So what is local compactness? So a topological space is said to be locally compact at X belongs to X if it has a compact neighborhood of X. Okay. So if for any point X, if you are taking from X comma tau, and if it has a compact neighborhood, then we say that a topological space is locally compact at that point X. Fine. Now, when we say that the space is locally compact, when if it is true for each of its point, then we say that it is the space is locally compact. Now, there is theorem on that. It says that let X tau be a Hausdorff topological space, then X tau is locally compact if and only if for each X belongs to X, there is an open set G containing X such that G bar is compact. Okay. Now, next, there is a theorem that says every closed subspace of a locally compact topological space is locally compact. Fine. So these are the theorems that have been discussed. Now there were some results like continuous image of a locally compact topological space is not necessarily locally compact, and a continuous open image of a locally compact topological space is locally compact. I hope you have gone through this theorems and its proof, and it is clear to you. So shall we proceed further? Okay. Now comes one point compactification. Okay. So what is it? So if you have let y tau be a housed of topological space. If you have a housed of topological space y comma tau, and y is expressed as x union point, that is infinity. Infinity does not belongs to x. Okay. So further, let we are defining a topology tau dash such that it is defined as open sets in X, G subset of X, such that G belongs to tau union Y minus K, such that K is a compact subset of X. Okay. So tau dash is formed by G, that is subset of X, and it belongs to tau union all Y minus K. Okay. So if this K is a compact subset, so if you are excluding this, so this part, and if you're taking union, so this thing forms our tau dash, that is a topology on Y. Okay. So what we are doing here is we were having a topological space X tau. We were having a topological space X tau. Now we have included a point that is infinity in X, and we form Y. Okay. So, and we have defined a topology on this Y by tau dash. Fine. Where Y tau will be a Hausdorff space. Fine. So this tau dash is forming a topology on Y. It has been proved in the lectures. And this Y comma tau dash is called as one point compactification of X tau. Okay. Because we have added one point in this X and formed Y. Okay. Which is forming like which is compact. So this Y comma tau dash is called as one point compactification of X tau. Okay. We will be discussing in detail about compactification at the end of the lecture. So, for the timing, I hope it is clear. Okay. Now, let y tau dash be one point compactification of Hausdorff topological space x tau. Then tau dash of x will be equal to tau. Okay. That means if you are forming a subspace topology tau dash on x, so that will be equal to what? This topology tau, which is already defined on x. Okay. Now next, let y tau dash be one point compactification of Hausdorff topological space x tau. Then y tau dash is compact. Okay. Now there were some results you might have gone through. Um then there was a local compact spaces, a characterization was discussed that says that let x tau be a Hausdorff topological space, then x tau is locally compact if and only for each x belongs to x, and for all open sets G containing x, there exists another open set. Okay, so let x tau be a Hausdorff topological space. Then x tau is locally compact if and only for each x belongs to x, and for all open sets G containing x. There exists another open set H containing x with compact closure H bar such that H bar will be subset of G. Okay, so there have been discussed such more. Now, what is these things have been discussed in the lecture. Then one more term that is a part of compactification, that is sequential compact sets. So what is it? So a subset of a topological space X is sequentially compact if and only if every sequence in A contains a subsequence which converges to a point in A. Okay. So is the definition clear to you? What is sequentially compact sets? So, okay. So I hope this, yes, yes, like real analysis. Okay. So let's start with the question answers. If this thing is clear. Okay. So the first question is that let A be a finite subset of a topological space X, then A is not sequentially compact, or A may be sequentially compact, or A is necessarily sequentially compact, or none of the above. So which of this will be true? As you have gone through the definition, so what will be the correct answer? Okay. So you're saying C. So I saw any argument that can you explain why? What will be the reason that A will be necessarily sequentially compact? Okay, ये compact है, that's why. Yes, so that we can form constant sequence. Okay, okay. So the argument is nearly correct. So the correct answer will be C. That is, A is necessarily sequentially compact. So why so? Here, as in the question, it has been given that A is finite subset of a topological space X. Okay. So here, for if S1 S2 is a sequence in A, then at least one of the elements, like say A naught, this will appear infinite times, right? Because this is a finite set. Okay, so if you are taking sequence, so at least one of the elements will appear infinite number of times. Okay, so this can form a subsequence of this kind, like A naught, A naught, A naught. So this will be constant sequence, which will converge to A naught only. Okay, and A naught belongs to what? In A. Okay, so um, by the definition, we can say that it is sequentially compact. Okay. So yes, the correct answer is C. That is, A is necessarily sequentially compact. Okay. So let's move to the next question. So the next question is that the open interval A is equal to 0, comma 1 as a real line R with usual topology is it sequentially compact, or may not sequentially compact, or is not sequentially compact, or none of the above? What will be the correct answer? Okay, you are saying C. What will be the reason? Um, you're saying because 0 and 1 does not belong to that. No, that won't be the reason. We are talking about sequentially compact and not about compactness. Here they are asking about sequential compact and not compactness. Okay. The definition is that a subset of a topological space X is sequentially compact if and only every sequence in A contains a subsequence which converges to a point in A. Okay. Then we say that of topological space is sequentially compact. Okay. So question is this. So what will be the answer? Hmm. Okay. So that means it won't be sequentially compact, right? Okay. Yes. So by that argument, we can say that it is not sequentially compact. Okay. So the correct answer is the how we can prove it. So consider, for example, the sequence Sn of this type 1 by 2, comma 1 by 3, comma 1 by 4, dot, dot, dot in A. So we can observe that this converges to what? 0. But therefore, every subsequence has also converges to 0. But 0 does not belongs to A. Okay. So we can say that the sequence Sn in A does not contain a subsequence which converges to a point in A. Okay. Hence, A is not sequentially compact. Fine. Okay. So I hope it is clear. So, okay. So let's move to the next question. So the next question is, consider a bounded closed interval A given by closed interval A comma B and B be an infinite subset of A. Okay. Then the question is it option A, that is B has an accumulation point P belongs to A, or B, that is B has an accumulation point P does not belongs to A, or C, that is A is not countably compact, or D, that is none of the above. Okay. So which will be the correct answer? Okay, so you are saying that correct answer will be A, that says B has an accumulation point P belong to A. So what about other options? How we will discard it and why option A is correct? Can you use supporting statements for this? Okay. Weierstrass property you are applying. Um, okay. By that you can say that option A will be correct. What about option C? Why it is not correct? That A is not countably compact. How to prove that? Okay. Take your time and let me know why option C will not be correct. Just think that A is bounded and it is a closed interval, and B is its infinite subset. So how can we prove that A is countably compact? What is the definition for countably compact? Yes. Okay, so you are saying that the reason may be that compact topological space is countable compact. Okay, this will work also. Okay, so the correct answer is A. That is, P has an accumulation point. P belongs to A. Okay. Um. So there is a definition for countably compact. Okay. Another definition. So what is it that we can apply? Also, the statement that you gave, that is worth it. So this way we can also justify that there is a definition that says a subset A of a topological space X is countably compact if and only if every infinite subset B of A has an accumulation point in A. Okay, so if you are taking any infinite subset B of A, it should have an accumulation point in that set A. Okay, then we say that our topological space is countably compact. Fine. And yes, there is Bolzano-Weierstrass theorem that says that every bounded infinite set of real numbers has an accumulation point. So by that, you will get that B is infinite subset of A. Hence, there is also B is also bounded since A is bounded. Therefore, by the Bolzano-Weierstrass theorem, B has an accumulation point P. Okay. Next, furthermore, since A is closed and the accumulation point of P of B belongs to A, that is by this definition of countably compactness that says if every infinite subset B of A has accumulation point in A. So here we got P that belongs to A. Okay. So we can say that our space is also countably compact. Okay. So this will be wrong. That says that A is not countably compact. Fine. Is it clear? The definition? Okay. So using this definition also, we can prove that the space is countably compact. Okay. So let's move to the next question. So the next question is state whether the following statement is correct or not. Okay. The statement is the open interval A equal to 0, 1 is countably compact. Is it true or false?
ये वो शायद मोटरसाइकिल बाहर उसका है ये बाहर है वो बाइक है भीतर में लगा हुआ
Yes. It is false. How? How can you prove that? How can we prove that it is false? Can you give me an example? Or if it is true, then also give me example. Okay. Yes, you can use the counterpositive statement, but apart from that, how can we prove it? Yes, by sequence. So, how can we prove it by using a sequence? What kind of sequence we need to form? Yes, yes. Okay. So let's see the answer part. So it will be false. How can we prove it? The open interval a equal to 0 comma 1 is not countably compact. Why? To consider the infinite subset b, we have taken it as 1 by 2, 1 by 3, 1 by 4. Okay. Now here b has only one limit point, that is 0, that does not belongs to a. Okay. Hence we can say that a is not countably compact. Okay. So your argument is correct. We can form this and we can prove it. Okay. So if it is clear, shall we move to the next question? Okay. So the next question is, let tau be the topology on n, that is natural number set, the set of positive integers generated by the following sets of this form, that is 1 by 1 comma 2, 3 comma 4, 5 comma 6, like that. Okay. And let a be a non-empty subset of n natural numbers. Okay. Then which of these options will be correct? Option A says that n comma tau is countably compact. B says that n comma tau is compact. C says that n comma tau is sequentially compact. And D says that all of the above. Okay. So which one of these options will be correct? Yes. So A we are taking, it will be helpful in proving about sequentially compactness. For sequentially compactness, you need a subset, right? So for that, we have taken A. So you can use it for proving or disproving option C. Are you sure? Just check. You have to give argument for all the answers, that A, B, and C, that all of these three are correct. Okay. So let me know one by one. Why do you think that n comma tau is countably compact, or it is compact, or it is sequentially compact? Okay, try to figure out what will be the correct answer. Yeah, take your time and let me know what will be the correct answer. Okay, just try it now. Okay, let's see one by one. For compactness, what do you need? You can just go by one by one. For proving that it is compact, what do you need? What is the definition of compactness in topological spaces? Yes, for if you have open subcover, okay. So you should give a sorry. If you have open cover, then you should get finite subcover. Okay, then we can say that it is compact. So in this case, that is n comma tau, where tau is defined in this form, like these are the open sets in our tau. So can you guess that what will be the open cover and can you find the subcover for that such that it covers natural numbers? Can you? Okay. Yes, union of n comma n plus 1, like what we have been given here also. That is 1 comma 2, 3 comma 4, like this, right? So this will form open cover, right? So can you get finite subcover for this so that it covers this natural? No, right? So will it be compact? Will it be compact? Okay. So in this way, we discarded this option, right? So this is discarded. So obviously it is not all of the above. So B and D is discarded. Now you have to think about option A and C. So let's go to option C. What it is? That is it sequentially compact? Is it sequentially compact? For sequentially compact, what do you need? You need a subsequence, okay, which is convergent in this, right? So is it sequentially compact? Sorry, that has a limit point in here. So is it sequentially compact? No. By A, it doesn't. A is just a non-empty subset. You can form it as you want. to prove either A or C. So for sequentially compact, what do you need? You need a sequence here which has a limit point. So do you, there is not, okay, let's see the answer. So correct answer is that it is countably compact. Okay. How can we prove that? How can we prove that it is countably compact? So yes, statement you have used is wrong. So shall we proceed with the solution part, or you want to think about it? Okay. So here A is a non-empty subset of n natural numbers. Okay. So let's consider a point n naught from A. Okay. Now if n naught is odd, here if n naught is odd, so this will form, that is n naught plus 1 will form accumulation point, right? That is limit point of A. And if n naught is even, that is if n naught is even, then this will form a limit point, right, of A by the definition of accumulation point of topological spaces of a subset. Okay. So in either case, A has an accumulation point. Fine. So whatever you take, you will get an accumulation point. Okay. And by the definition that we have discussed for countably compact, this definition that a subset of a topological space is countably compact if and only if every infinite subset B of A has an accumulation point. Okay. So here, whatever subset you take, you will always get an accumulation point, right? Hence, this n comma tau will be countably compact. Fine. On the other hand, this is not compact. Why? Because as we show that every open cover here does not have a finite subcover. Okay. Furthermore, n comma tau is not sequentially compact. Why? Because if you are taking the sequence 1, 2, 3, d dot dot dot, this contains no convergent subsequence. Okay. Fine. Hence, this will also be not true. Got it? Nee, for proving convergent sequence, sorry, sequentially compact, you have to form the sequence, and here countably compact, we just need that it should have a accumulation point, right? So I hope it is clear. Okay. Shall we move to the next question? Okay. So the next question is, let X tau be countably compact topological space, then it is sequentially compact. First option is sequentially compact. Second is compact. So which of these options will be correct? Is it option A that is only first, or B that is only second, or C that is both 1 and 2, or D that is neither 1 nor 2? So which of these options will be correct? Yes, by the previous question, we can directly say that both are false. Okay. Yes. So by using the previous question, you have this statement that if X tau is a countably compact topological space, then it won't be sequentially compact and it won't be compact also. Okay, we cannot say that it is sequentially compact or it is compact. Okay, let's move to the next question. Okay, so before moving to the next question, let us discuss about what is compactification. Fine. So, as you were asking to discuss about one-point compactification. So before that, first let us discuss about what is compactification. Okay. So a topological space X is said to be embedded in a topological space Y if X is homeomorphic to a subspace of Y. Okay. Again, I'm reading. So a topological space X comma tau, if you are taking a topological space X comma tau, so you will say that this is embedded in another topological space Y comma tau dash say if X is homeomorphic to a subspace of Y. Okay, so if you are taking a subspace of Y and if X is homeomorphic to that, then we say that this X comma tau is embedded in this topological space Y comma tau dash. Okay. Furthermore, if Y is a compact space, then Y is called a compactification of X. Okay. Okay. Furthermore, if Y is a compact space, then Y is called a compactification of X. Fine. So in this such situation, we say that um, X is embedded in Y, and if this space is compact, then we say that Y is a compactification of X. Okay. So frequently, the compactification of a space X is accomplished by adding one or more points to X. Okay, so if you add one or two points or more points in X and form a new space, then in this way we form the compactification. Okay, and then defining an appropriate topology on the enlarged set. Okay, so you will first add some points in X and then we will define a topology tau dash on that enlarged set. Okay, so that the enlarged space is compact. So whatever the enlarged space you get, that should be compact and contains X as a subspace. Okay, since you have added points in X, so obviously it will be containing X. Okay, in this way you form the compactification of a space X comma tau. Okay, yes. So
Ma'am, so we are adding only one point in one point compactification or more than one point in compactification.
yes, one point compactification is kind of like generalizing. You are taking one kind of example to that. Okay, particular case you can say.
Okay, ma'am.
Understood. So let's discuss it with the help of a few examples. So in the real line, uh, consider the real line R with the usual topology U. Okay. So we join two new points. We are adding two new points to R, denoted by infinity and minus infinity to R. Okay. So you are adding two new points. So you will get an enlarged set, right? We are denoting it with R star. Okay. So you got R star as R union minus infinity and infinity. Okay, this is what our extended real line. Okay, you know about it. Fine.
Yes, ma'am.
Okay. So the order relation in R can be extended to R star by defining, you know about order relation, right? Like this A, if you have 2 points A and B, so it is ordered like this, A less than B, right?
Yes, ma'am.
So by
Yes, ma'am.
defining in this way, minus infinity less than A less than infinity for any A belongs to R, you can define the extended real line, right? So the class of subsets of R star of the form, what are the kind of subsets of R star? Like it can be open interval A comma B. It can be defined like all the elements X in between A and B, right? Or open at A and closed at infinity. So why are we writing here closed at infinity? Because we are including this point infinity in our R. In R, it is not there, okay? So generally we write it like this, right?
Yes, ma'am.
But here we are in the extended real line, we are including this point. So here we will write it as closed. So this will contain all the X such that A is less than X, okay? Similarly, for minus infinity also, we can write it like this, that closed at minus infinity and open at A. Okay, so this will contain points in this form like X such that X is less than A. Okay, so this kind of class of subsets of R star, this will form a base for a topology U star. Okay, as we said here that in a topological space x comma tau, we will be adding few points. We will form a new topological space y comma tau dash, where y will be what? Compact, right? And x will be subspace of that. And what more? Okay. So these are the points, right? So here, one more thing, that this should be compact also. So here, and we will form the new topology on the extended whatever topology is. So here the extended topology, extended space is R star. So we are forming the topology U star on R star. Okay. So this will form this kind of sets, a class of subsets of R star can form a base for topology U star on R star. Okay. This you can use for forming the basis. Okay. Furthermore, R star comma U star is a compact space. Fine. This is compact. Why? Because it is closed
Yes,
and
ma'am.
bounded. You can see that. And also it contains R comma U, that is our original space, R comma U, as a subspace. So you can see that it is a compactification of R comma U. Okay. So here we saw that R star comma U star is forming compactification of R comma U. Fine. Is it clear how we
Yes,
are
ma'am.
forming the compactification? Okay. Just take a moment and look into it. If you have any doubt, you may ask. The definition part.
Ma'am, please next slide. Ma'am, Here we are saying that A open A closed infinity is a compact set.
Yes, yes. No, open A,
Okay.
not A, open A, not open A. This R star comma, this R star is forming a compact space. These will form the basis. Okay, this will form the class of
Okay.
subs. You
So
can
A infinity and minus infinity to A, these are the bases for R
yeah,
star.
yeah, you can use this class of subsets for forming the basis. Okay, like we do for R.
Okay, ma'am.
Uh, is it clear now?
Yes, ma'am.
Shall we proceed?
Yes, ma'am.
Still having any doubt? Okay,
Um,
just see to it. And if it is clear, then we will move to the one. We will take one more example on it. Is it clear?
yes, ma'am.
Okay. So let's take one more example on this. You may be familiar with this.
Yes, ma'am.
Yeah, in complex analysis. So let's see there. Here also compactification works. So let's see this. So let's see denote the xy plane in the Euclidean three space R3. So this is the xy plane. We are this xy plane. We are denoting it with C. Okay, in the three space R3. So this is R3 space, and let us denote the sphere with center 0, 0, 1. Okay, so this is the sphere S. It is centered at this. This is 0, 0, 1. Okay, that is on z axis. It is centered at 1, and it is having a radius 1. So it will go till here, that is 0, 0, 2 on the z axis, and here on 0, 0, 0. Fine. Now here, the line passing through the north pole, that is this 0, 0, 2, we are taking it as infinity. Okay, we are taking this point as infinity, denoting it by infinity, that is given by 0, 0, 2. This belongs to sphere, right? So if you're taking passing any line through this point, so where it will cut on the sphere, it will cut only at one point, right? If you're
Yes, ma'am.
taking the point from inside, line from inside, so it will cut the sphere at one point, at here, and then it
Ma'am, we are
intersects. Yes.
using here projection or something else.
No, no, no. Here we are not using projection. Here
Okay,
we
ma'am.
are having a sphere, okay? So sphere, you can imagine it as a 3D, right? So from a sphere, from this point 0, 0, 2, you are passing a line, okay? So if this line is going from this sphere, from the inside, so it will eventually cut this sphere at one point, right? Wherever you take, here or here you take, or here
Yes,
you
ma'am.
take, anywhere. you take, it will cut the sphere only once, right? After
Yes, ma'am.
that, that line will pass through which point? At this point P, right? This, it will cut this plane C also, right? At some point P. Okay. So can you visualize it till now?
Yes, ma'am.
Okay. So what, let me repeat it again. So the line passing through the North Pole, infinity, that is given by 002, belonging to S, and any point P belong to C, intersect the spheres S at exactly one point P dash. Okay. So it will intersect the sphere at exactly one point P dash. Okay.
Yes, ma'am.
So distinct from infinity, distinct from this point. So we are defining a function f from C to S. Define a function f from C to S, from this plane C to sphere S. Okay. So what you are saying here, that every point f of P, okay, P is mapped to some point P dash on the sphere, right? So f of P will be what? P dash. Fine. So here let f be from C to S be defined by f of P is equal to P dash. Then f is in fact a homomorphism from the plane C1. From the plane C.
Ma'am, every point belonging to the complex plane in matlab, this plane mapped to P dash 002.
No, no, no. Every point on this plane C is mapped to P dash. Okay. We are not talking about 002. We are taking a line from 002 and it will cut somewhere P dash on the sphere, and then it will cut somewhere on C, that is P.
P dash the
Okay.
point on the sphere.
Yes, yes. P
Okay,
dash.
ma'am. Okay.
Other than
Clear.
this 002 or infinity. Okay. Other than this point.
Yes, ma'am. Okay, got it.
Yes. So will this form a homomorphism? This F will form a homomorphism?
Yes, ma'am.
Okay. It will form the homomorphism. Now, then F is in fact a homomorphism from this plane C, which is not compact. Okay. Is C compact? No, right? C is not compact
Yes, ma'am.
because
Not
it's
complete.
not bounded. Okay.
Yes, ma'am.
On to it is so F is from C, which is not compact, onto what? S, right? Onto the subset S minus infinity of the sphere. So this is mapping to S minus infinity. Means if you are excluding this point, infinity. Okay. Of the sphere. And S is compact. But if you are taking S,
Ma'am, please repeat from the where we say that this is not compact.
okay. See, here F is homomorphism, right? C is not compact.
Yes,
C
ma'am.
is
Till
not
there.
compact.
Yes, ma'am.
This is mapped onto the subset S. If this is sphere S, this contains everything, right? Now take its subset S minus infinity. Okay. S minus
Okay,
infinity.
ma'am.
If you are excluding one point, so this will form a subset of S, right?
Yes, ma'am.
Yeah. So which is not compact onto the subset S minus infinity of the sphere S. But S is what? S is compact, right? If you're taking whole sphere,
Yes, ma'am.
sphere is compact, right?
S is compact.
So here what we have got, um, okay, now see, S minus infinity, this is not compact, but S is what? Compact, right? Now, what is the definition for compactification? What do we do? If you are considering this
Now we
point,
add
if you are considering this set S minus infinity, okay, add one term infinity in this, so it will form what? S. Okay. So
yes, ma'am.
we have extended this, right, to S. Also, whatever we have extended, this is now compact also. Okay, so this is the original one which we have extended to S, and now S is what? Compact. Okay, so is it
Ma'am,
satisfying? Yeah.
I am not getting why S minus infinity is not compact.
S minus infinity is, huh, this is not compact. Why? Because this is forming homeomorphism, right?
Okay, okay, ma'am. Now got it. We are using concept of the homeomorphism here.
Yeah.
Okay, ma'am.
So, okay. So this is not compact, and when we add one element, so this becomes compact, right? So what we
Yes,
have
ma'am.
done, we have extended the our space and formed the compact space. So we have done the compactification, right?
Yes, ma'am.
So can we say that S is the compactification of S minus infinity, right?
Yes, ma'am.
But this is homeomorphic to what?
C.
C. Okay. So we can say that S is a compactification of C. Fine.
So we can map whole C onto
Onto
S.
this sphere S. Okay.
Okay, ma'am.
So this is there in complex also. Its name I'm not recalling.
I am also not getting, ma'am. What's
It's,
the name?
it's a kind
Stereographic
of
projection.
stereographic projection. Okay.
Yes, ma'am.
So I hope it is clear how we can link the compactification to this part, right?
Yes, ma'am.
Similarly, we can do for one point compactification also. So shall I repeat that definition of one point compactification?
Yes, ma'am. If you want to, but now I got it.
Okay. Okay, just let's go through it once more and then we will proceed to the next question. Okay, so here also you can see X tau is the Hausdorff space and we have formed a space Y by X union infinity where infinity does not belongs to X. Further, we have defined topology tau dash on Y. Okay, so in this way we have extended space X to Y by adding one point infinity. Okay, and we have formed a topology also on that. And whatever we have formed, this is compact also. Okay, so this is said to be a one point compactification of X tau. Fine.
Yes, ma'am.
Okay. Okay, so if it is clear, so let's move to the next question. So the next question is state whether the following statement is true or not. So statement is if X is sequentially compact, then X is also countably compact. Is it true or false? And also justify it.
Ma'am, I think it is false.
And why so? Justify it.
Ma'am, uh,
Just try.
okay, ma'am. Thinking, ma'am.
Let's do it.
Ma'am, if we have sequentially compact, then there exists a sequence
Hmm.
in that set which is converging in that, let's say A.
So
So, ma'am, am I in the right direction or not?
yes, yes. Try it.
It is true. We
It
can
is
prove
true.
this.
Yes, you have proved it, right? It is true, right? So confirm,
Yes,
is
ma'am.
it
By
is true?
taking a sequence,
Yes, continue.
yes, ma'am. I'm telling that we can take a sequence
Yes.
which which is which has a subsequence
Yeah.
converging to some
Some
point.
point. So it will automatically eventually form what? Accumulation point, right?
Yes, ma'am. Limit point, or we can
Huh.
say.
So that will imply that it is countably compact, right? So it will be
Yes, ma'am.
true. Confirm, right?
Yes, ma'am.
Okay, so it is
Think
true. Is there any doubt?
no, ma'am.
Okay, so it will be true. How we will prove it? So let A be any infinite subset of X, then there exists a sequence A1, A2 in A with distinct terms, right? Since X is sequentially compact,
Yes, ma'am.
so it will have a subsequence which converges to a point P belongs to X, right? Hence, every neighborhood of P contains an infinite number of terms of convergent subsequence AIN, right? So if you have a convergent
Yes, ma'am.
subsequence, so it will contain an infinite number of terms of it. But these terms are what? Distinct. Hence, every neighborhood of P contains an infinite number of points in A. Okay. So accordingly, P will form what? Accumulation point of A. Hence, we get that X is countably compact. Fine. So if X is sequentially compact, this implies that it is also countably compact. Fine.
Yes, ma'am.
So this is it. These were the
Presentation over.
questions. Yeah. So if you have any questions or any doubts related to any of the questions discussed or mm, any of the topics, so you may ask about that.
No, ma'am. Till till no doubt.
Okay, so everything is clear to you.
I'll let you know in the next week, ma'am, because I have some work in this week, so I can't do.
Okay, so you haven't gone through the like topics, right?
Yes, ma'am. So I'll let you know in the next week.
Okay. So other things like you asked about one point compactification and whatever like Lebesgue lemma, uniform continuity and even space. Have you gone through this part?
Yes, ma'am. I have gone the lectures of this week, but not the previously I have done, in which I have a doubt.
Okay, okay, okay. So the questions that you want me to discuss or topics you want me to discuss.
Yes, ma'am. But
Okay,
this week I have done complete all the lectures.
okay. So maybe these things you are being clear with, right? And about T1, T naught spaces, it is there in the next week, right?
Yes, ma'am. Separation axioms in the next week.
Okay. So if all this part is clear, then fine. And if you have doubt, then you may ask.
No doubt, ma'am.
So if you don't have any doubt, let's go through the topics from the week. The results. So here there were some results from limit point compactness that if what the definition of limit point compact, so the results like every compact topological space is limit point compact, but the converse is not true. Okay, so you may form examples, find examples or counter examples to prove that the converse part of this, that is not true, that if the every limit point compact set is not compact topological space. Okay, and continuous image of a limit point compact topological space need not be limit point compact. So here in one example that we have seen, mm, yeah, so example, so here the example was that let X tau be countably compact topological space, then it is sequentially compact or compact. So we saw that both are not true, but if it is compact or countably compact, sorry, sequentially compact, then in both these cases it is countably compact. Okay, so this is true, but vice versa it is not true. We have seen it through the examples as well. And some more results in this form you can see here. Mm, about 1 point compactification, that let white tau dash be 1 point compactification of locally compact Hausdorff topological space, then white tau dash is Hausdorff. regarding Hausdorff spaces. And if y tau dash be one-point compactification of locally compact Hausdorff topological space, then it is unique up to homomorphism. So these all things have been discussed in the class. So if you have any doubts regarding previous classes also, or any topic or an example you want me to discuss, so please let me know so that we will be discussing it in the next class. And thank you for joining. So if you don't have any doubt, you may leave. We will be meeting in the next class. And if you have doubt, you may ask.
No, ma'am, thank you so much for the session.
Okay.